there is a wall. Not a wall you can see, not a wall made of stone or steel or any material we have ever touched. A wall built into the fabric of reality itself, written into the equations that describe how the universe works, enforced by physics without exception, without negotiation, without any path around it. The wall is the speed of light, and it does not care about your technology. It does not care about how advanced your civilization is. It does not care about how much energy you can generate, how clever your engineers are, how badly you want to cross it. It is not a wall that falls when you hit it hard enough. It is a wall that becomes more expensive to approach with every meter per second you gain. This is not a story about the current limitations of human technology. It is not a story about what we cannot do yet, but will be able to do eventually. It is a story about what the universe has built into itself, the physical constraints that apply to any civilization, anywhere, at any level of technological development, now and forever. Understanding why interstellar travel is so brutally difficult, not just for us, but for anyone, requires starting from the beginning, from the actual numbers, from the physics that is not going to change. If the night is long, stay. Start with the distances. The nearest star to our Sun is Proxima Centauri, 4.24 light-years away. A light-year is the distance light travels in 1 year. Light moves at approximately 299,792 kilometers per second, fast enough to circle the Earth 7.5 times in a single second, fast enough to reach the Moon in about 1.3 seconds, fast enough to reach the Sun in about 8 minutes and 20 seconds. In 1 year, light travels approximately 9.46 trillion kilometers. Proxima Centauri is 4.24 of those units away. That is approximately 40 trillion kilometers.
40,000 billion kilometers. The number is so large that it resists intuition. It is not the kind of number the human brain evolved to process directly. Let us try to make it concrete. The fastest spacecraft humanity has ever launched is Voyager 1, currently moving at approximately 17 kilometers per second, roughly 61,200 kilometers per hour. Voyager 1 has been traveling since 1977. As of today, it has covered approximately 23 billion kilometers, the farthest any human-made object has ever traveled. At Voyager 1's current speed, pointed directly toward Proxima Centauri, the journey would take approximately 73,000 years. 73,000 years. Anatomically modern humans have existed for roughly 300,000 years. The entirety of recorded human history, from the first writing systems to this moment, spans approximately 5,000 years. Voyager 1's journey to the nearest star would require more than 14 times all of recorded history. And Proxima Centauri is the nearest star. It is the minimum. The galaxy is 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.537 million light-years away. The observable universe extends approximately 46 billion light-years in every direction. The distances are not a practical obstacle that better engineering will eventually overcome. The distances are a fundamental feature of how space is structured. Now think about what it would actually take to cross even the nearest of these distances in a time frame meaningful to human experience, in decades rather than millennia. To reach Proxima Centauri in 42 years, a spacecraft would need to travel at 10% of the speed of light, approximately 30,000 kilometers per second. This is roughly 1,800 times faster than Voyager 1. It is a speed that no human technology currently in existence or under development can remotely approach. But let us assume it is achieved. Let us ask what the physics actually demands of any system capable of this. The first demand is energy. The kinetic energy of an object depends on its mass and its velocity. As velocity increases, kinetic energy increases, and at relativistic speeds, the relationship between velocity and energy becomes increasingly steep. For a spacecraft with a dry mass of 1,000 metric tons, a modest vehicle capable of sustaining human life for a multi-year journey, reaching 10% of the speed of light requires kinetic energy of approximately 4.5 times 10 to the 21st power joules. To put that number in context, global human energy consumption in 2023 was approximately 6 times 10 to the 21st power joules. Accelerating a single 1,000-ton spacecraft to 10% of light speed requires roughly 75% of all the energy used by every human being on Earth in an entire year. And this is with perfect efficiency, 100% conversion of fuel energy into kinetic energy of the spacecraft, with no losses whatsoever.
Real propulsion systems do not achieve 100% efficiency. Current best estimates for advanced nuclear propulsion systems suggest efficiencies in the range of 50 to 60% under ideal conditions. The actual energy requirement is therefore larger by a factor of 2 or more. That covers acceleration only. To stop at the destination requires the same energy again. A round trip requires roughly 4 times the one-way acceleration energy. The energy budget for a round-trip crewed mission to Proxima Centauri at 10% of light speed exceeds annual global human energy production several times over. But this still understates the problem dramatically because it ignores propellant. A rocket works by expelling mass. The expelled mass carries momentum in one direction. The spacecraft carries momentum in the other direction. The efficiency of this exchange depends on how fast the propellant is expelled, the exhaust velocity.
The higher the exhaust velocity, the more efficient the rocket. The relationship between the mass of propellant required and the final speed achieved is described by the Tsiolkovsky rocket equation. In its simplest form, the mass ratio, total mass including propellant divided by dry mass, grows exponentially with the ratio of final velocity to exhaust velocity. For a nuclear fusion rocket operating near its theoretical limits, exhaust velocity of perhaps 10% of the speed of light, the mass ratio for achieving 10% of the speed of light is approximately e to the power of 1 is approximately 2.7. That means propellant mass roughly equal to dry mass. That sounds manageable. But this assumes we can build a fusion rocket with exhaust velocity equal to 10% of the speed of light, something that has never been demonstrated and faces enormous engineering challenges. More realistic fusion rocket exhaust velocities are significantly lower, perhaps 5 to 6% of the speed of light at best.
At exhaust velocity of 5% of the speed of light, reaching a final speed of 10% requires a mass ratio of E squared approximately equals 7.4. For every ton of spacecraft, roughly 6.4 tons of propellant. A 1,000-ton spacecraft requires approximately 6,400 tons of propellant. But those 6,400 tons of propellant also need to be accelerated, which requires more propellant to carry the propellant. The rocket equation compounds. The actual launch mass grows substantially beyond the naive calculation. And deceleration. The spacecraft must slow down at the destination. If it carries propellant for deceleration, that propellant must also be accelerated from the start, compounding the mass ratio further. Some mission architectures involve decelerating using a laser array or a magnetic sail interacting with the interstellar medium at the destination, removing the need to carry deceleration propellant. But these approaches add their own enormous technical challenges.
The propellant problem is one of the most severe constraints on interstellar travel. It does not go away with better technology. It is baked into the mathematics of momentum conservation. Now let us talk about what 10% of the speed of light actually means physically for a spacecraft traveling through interstellar space. Interstellar space is not empty. Between the stars there is gas, primarily hydrogen, but also helium and trace amounts of heavier elements. There is dust, microscopic particles of silicate and carbon compounds, ranging in size from nanometers to micrometers. The average density of the interstellar medium in our part of the galaxy is approximately 1 atom per cubic centimeter, extraordinarily sparse by any everyday standard. But at 10% of the speed of light, that sparseness becomes catastrophic. When a spacecraft moves at 30,000 kilometers per second, every atom in its path strikes the leading surface with an energy determined by relative velocity. An interstellar hydrogen atom, a single proton, hitting the spacecraft at 10% of the speed of light, has a kinetic energy of approximately 4.7 mega-electron volts. That is in the range of high-energy alpha particles produced by radioactive decay, particles that are themselves considered ionizing radiation, hazardous to biological tissue and electronics. A spacecraft with a frontal cross-section of 10 square meters moving at 10% of light speed through the interstellar medium at average density will encounter approximately 3 times 10 to the 18th power hydrogen atoms per second, each carrying roughly 4.7 mega-electron volts. The total power deposited in the leading surface is on the order of megawatts. This is not a gentle drizzle of particles.
This is a continuous high-energy particle bombardment of the spacecraft's leading edge at power levels comparable to industrial heating equipment. The structural implications are severe. Materials subjected to continuous high-energy particle bombardments suffer radiation damage, atomic displacements in crystal lattices that accumulate over time, leading to embrittlement, reduced structural integrity, and eventually catastrophic material failure. For a 40-year journey, the cumulative damage to unshielded structure would be enormous. The biological implications are worse. High-energy particles passing through biological tissue produce ionization, the ejection of electrons from atoms along the particle track. This ionization damages DNA directly and produces reactive chemical species that damage it indirectly. The body has repair mechanisms for DNA damage, but these mechanisms are not perfect. They have an error rate.
Cumulative radiation exposure beyond certain thresholds overwhelms the repair mechanisms and causes cancer, immune dysfunction, and other radiation-related illness. On the International Space Station, astronauts receive radiation doses roughly equivalent to a few chest X-rays per day, significantly elevated above Earth's surface, but manageable for missions of several months with careful monitoring. On a trajectory to Mars, outside the protection of Earth's magnetic field, the dose rate is roughly 5 to 10 times higher. For a 40-year interstellar transit, accumulated radiation doses would be many times the lifetime limits considered acceptable for Earth-based workers in radiation environments. The solution is shielding. But shielding has mass, and mass that must be accelerated from the start requires more propellant, which requires more mass, which requires more propellant. The rocket equation compounds again. Water is one of the better shielding materials for high-energy particles because its hydrogen content provides mass per unit volume that effectively slows particles through collisions. A shield of water several meters thick around a habitat module would significantly reduce the dose rate to the crew. But several meters of water covering a habitat module adds thousands of tons of shielding mass. The scaling is brutal. Every improvement in one parameter, speed, crew size, mission duration, shielding, makes the mass budget worse, which makes the energy budget worse, which makes the propellant requirement worse. There is no elegant exit from this cascade. It is the physical reality of trying to move mass at a significant fraction of the speed of light through a medium that is not quite empty. Now let us go deeper into the relativistic physics, because at significant fractions of the speed of light, the familiar Newtonian picture breaks down, and the universe starts behaving in ways that are counterintuitive but precisely measured. Special relativity, Albert Einstein's 1905 framework describing the relationship between space and time for objects in relative motion, makes 3 predictions that are directly relevant to interstellar travel. The first is time dilation. For an observer moving at velocity v relative to a stationary reference frame, time passes more slowly by a factor of gamma equals 1 over the square root of 1 minus v squared over c squared, where c is the speed of light. This factor, the Lorentz factor, equals 1 at rest and increases without bound as v approaches c. At 10% of the speed of light, gamma is approximately 1.005, essentially no time dilation. A 42-year journey is a 42-year journey for the crew. At 50% of the speed of light, gamma is approximately 1.15, modest time dilation. The crew ages about 87% as fast as Earth-based clocks. At 90% of the speed of light, gamma is approximately 2.29, significant time dilation. The crew ages at less than half the rate of Earth clocks. A 40 light-year journey that takes 44 years by Earth clocks takes about 19 years by the crew's subjective experience. At 99% of the speed of light, gamma is approximately 7.09. The crew ages at about 1/7 the rate of Earth clocks. At 99.9%, gamma is approximately 22.4, 1/22nd the rate. At 99.9999%, gamma is approximately 707. The crew barely ages. This is physically real. It has been measured in particle accelerators, in atomic clocks flown on aircraft, in the precise timing corrections required by GPS satellites. Time dilation is not a theoretical curiosity. It is an experimentally confirmed feature of the universe. And it seems to offer a seductive possibility for interstellar travel. Travel at a large enough fraction of the speed of light, and subjectively, short journeys become possible to very distant destinations. The crew of a spacecraft at 99.9999% of light speed could travel to the center of the galaxy, approximately 26,000 light years, in a subjective crew time of about 37 years. They would return to Earth to find it 52,000 years in the future, but from their perspective, the journey took a human lifetime. The problem is what it costs to get there. The kinetic energy required for a 1,000-ton spacecraft at 99.9999% of the speed of light is E equals gamma minus 1 mc squared equals 707 minus 1 times 10 to the 6th power kilograms times 3 times 10 to the 8th power meters per second squared approximately equals 6.35 times 10 to the 26th power joules. The Sun's total power output, the luminosity of our star, radiating in all directions into space, is approximately 3.8 times 10 to the 26th power watts. The energy required to accelerate this single spacecraft is roughly equivalent to the total energy the Sun radiates in about 1.7 seconds. The Sun's entire 1.7 second energy output for one spacecraft, one way. This is the energy of a Type II civilization on the Kardashev scale, a civilization that has successfully harnessed the entire energy output of its star. No such civilization has ever been observed. We have not even achieved Type I, which involves harnessing the full energy resources available on a single planet. The second relativistic effect relevant to interstellar travel is length contraction. At velocity v,
distances in the direction of travel appear contracted to a moving observer by a factor of gamma. At 90% of the speed of light, the distance to Proxima Centauri shrinks from 4.24 light-years to about 1.85 light-years from the spacecraft's frame of reference. At 99.9999%, 4.24 light-years becomes about 0.006 light-years, roughly 57 billion kilometers, a distance the spacecraft covers in a subjective time of about 2 days. This sounds extraordinary, but length contraction does not reduce the energy required. The energy still scales with gamma, just as time dilation does. The mathematics of special relativity ensures that the subjective efficiency of high-speed travel cannot be exploited to circumvent the energy barrier. You can arrive quickly from the cruise perspective, you cannot arrive cheaply. The third effect is the increasing resistance to acceleration as velocity approaches c. In Newtonian mechanics, force equals mass times acceleration, and the relationship is linear: double the force, double the acceleration, regardless of current velocity. This intuition breaks down completely at relativistic speeds. At relativistic velocities, the effective inertia of an object increases by a factor of gamma. The faster an object moves, the harder it is to accelerate further, not because of any mechanical friction, but because of the fundamental geometry of spacetime. To continue accelerating a spacecraft toward the speed of light requires force proportional to gamma times the acceleration, and gamma grows without bound as velocity approaches c. This is why no amount of energy can push a massive object to exactly light speed. The energy required to reach the final increment of velocity, from 0.9999 c to c, for example, is infinite. Not very large, infinite. The speed of light is not an engineering barrier. It is a mathematical limit baked into the structure of space-time. This is the first wall the universe built. Now let us examine the second wall, the one that operates at any speed, not just relativistic ones, the interstellar medium. We established that hydrogen atoms strike a fast-moving spacecraft as high-energy particles. But the interstellar medium also contains dust grains, solid particles ranging from nanometers to micrometers in diameter, composed of silicates, carbon compounds, and other materials.
At 10% of the speed of light, a dust grain 1 micrometer in diameter, roughly the size of a large bacterium with a mass of approximately 10 to the minus 15 kilograms, strikes the spacecraft with kinetic energy of approximately 4.5 times 10 to the minus 4 joules. That sounds small, but consider, a rifle bullet strikes with roughly 2,000 to 5,000 joules of energy. The ratio of energies is about 10 million to 1. The ratio of masses, however, is roughly 10 billion to 1. Pound for pound, or rather gram for gram, the dust grain impact delivers far more specific energy than the bullet. At a scale more relevant to spacecraft integrity, a millimeter diameter dust grain, a barely visible speck, at 10% of light speed carries approximately 450 joules of kinetic energy. A centimeter diameter particle, still small enough to be nearly invisible, carries 450,000 joules, roughly equivalent to a stick of dynamite. The number density of such particles in the interstellar medium is low.
Millimeter-sized grains are rare, but a spacecraft traveling 40 trillion kilometers through the interstellar medium will encounter statistics, not individual events. In 42 years, at 10% of light speed, even rare events become probable. Mission planners have proposed various solutions to the dust grain problem. The most straightforward is a sacrificial shield, a thick layer of material placed at the bow of the spacecraft designed to absorb and vaporize incoming particles. The spacecraft flies behind its own debris cloud, protected from direct impacts. But a shield capable of stopping millimeter-sized particles at 10% of light speed must be extremely massive. The energy of each impact must be dissipated within the shield material without penetrating through to the spacecraft structure behind it. Materials science sets limits on how efficiently energy can be absorbed per unit mass. The required shield mass is substantial.
At higher speeds, the dust grain problem becomes categorically more severe. At 50% of light speed, a 1 millimeter grain carries 6,000 times more energy than at 10%. The shield must be correspondingly thicker and correspondingly more massive. There is no solution to the dust grain problem that does not involve either very large shields, very slow speeds, or active mitigation systems that identify and destroy incoming particles before impact. Active systems require enormous pointing accuracy and response times measured in microseconds at these velocities. Passive shields grow the mass budget to problematic sizes. Slow speeds eliminate the time dilation benefits that make relativistic travel appealing. The interstellar medium is not empty space that can be treated as a vacuum for engineering purposes. It is a diffuse but physically significant environment that exerts real constraints on any spacecraft attempting to traverse it at a significant fraction of the speed of light. Now let us move to the third wall, the one that attacks the spacecraft from the front, regardless of what it is made of. At velocities approaching the speed of light, the spacecraft is not simply striking particles in the interstellar medium. It is blue-shifting the electromagnetic radiation it encounters. The cosmic microwave background, the relic radiation left over from the Big Bang, permeating all of space at a temperature of 2.7 Kelvin, produces photons with wavelengths in the millimeter range. These photons are entirely harmless to any material or biological tissue at their natural energy. But for a spacecraft moving at a large fraction of the speed of light, the Doppler effect blue shifts these photons. At 90% of light speed, the Lorentz factor of about 2.3 shifts the peak of the cosmic microwave background from millimeter wavelengths to sub-millimeter wavelengths. Slightly energetic, but still low energy. At 99% of light speed, the Lorentz factor of about 7 shifts the peak into the infrared. At 99.9%, gamma is approximately 22, and the peak shifts into ultraviolet. At 99.99%, gamma is approximately 71, and the peak reaches soft X-rays. At sufficiently high velocities, the cosmic microwave background, harmless starlight at rest, becomes a lethal radiation environment. The entire universe is glowing with X-rays and gamma rays from the perspective of a rapidly moving spacecraft. There is no shield against this that does not involve enormous mass, because the radiation is coming from every direction, not from a localized source. This sets a practical upper limit on travel speed that is more stringent than the energy barrier alone. Even if a civilization somehow managed to generate the astronomical energies required for 99.9% of light speed, the resulting radiation environment from blue-shifted cosmic microwave background might make the interior of the spacecraft lethal to any biology. The universe has layered its barriers carefully. The energy barrier operates at all speeds. The dust grain barrier intensifies with speed. The radiation barrier from the blue-shifted cosmic background imposes an effective ceiling that may be below 99% of light speed for biological travelers. Let us now think about what happens when we try to circumvent these barriers through proposed exotic mechanisms, the ideas that science fiction has made familiar and that serious physicists have occasionally put on paper, if not in laboratories. The first is the Alcubierre drive. In 1994, Mexican physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity demonstrating that the equations of general relativity, the theory describing how matter curves spacetime, admit a class of solutions in which a region of space contracts ahead of a spacecraft and expands behind it. The spacecraft sits inside a stable, flat region, a bubble, while spacetime itself flows around it. From outside, the spacecraft appears to move faster than light, but locally, within its bubble, the spacecraft is stationary. It does not accelerate through space, space moves around it. This is genuinely elegant mathematics. Einstein's equations do not forbid faster than light travel by this mechanism because no individual object ever locally exceeds the speed of light. It is the metric of spacetime that changes, not the spacecraft's velocity relative to its local surroundings. The physical requirements for this solution, however, are catastrophic. The Alcubierre metric requires a region of negative energy density, exotic matter,
to maintain the contracted region of space ahead of the bubble. Negative energy density means matter with energy less than that of the vacuum, a concept that has no macroscopic classical analogue. Quantum effects can produce small regions of negative energy density, as in the Casimir effect between closely spaced conducting plates. But the amounts are microscopically small. Alcubierre's original calculation of the required negative energy was staggering, on the order of the total mass energy of Jupiter, negative. Later refinements by Harold White and others at NASA reduced this estimate, but even optimistic current calculations require negative energy equivalents that are many orders of magnitude beyond anything achievable. There is also a causality problem. The occupant of an Alcubierre bubble cannot manipulate the bubble from inside. The geometry means that no signal from inside can reach the bubble wall to control it. The bubble must be established and controlled from outside. But the entire point of the drive is to take the occupants somewhere, which means the drive must be set up in advance at the destination before the journey begins. The mechanism is useless for exploration. Additionally, detailed analysis of the Alcubierre metric shows that the bubble would accumulate radiation from the interstellar medium as it propagates, a growing shell of high-energy particles that, upon the bubble's deceleration at the destination, would be released into the surrounding region. The destination environment might be destroyed by this radiation burst. The Alcubierre drive is a mathematical solution that satisfies Einstein's equations while violating every known physical constraint on the materials required to implement it. The second proposed exotic mechanism is the wormhole. Wormholes, formerly Einstein-Rosen bridges, were first described by Einstein and Nathan Rosen in 1935 as a theoretical consequence of general relativity. They represent topological connections between distant regions of spacetime, tunnels through which travel might be possible in far less time than traversing the normal distance between 2 points. The mathematics is real. General relativity's equations do admit wormhole solutions, but the physics is deeply problematic. Wormholes are intrinsically unstable. Without some mechanism to hold them open, a wormhole throat collapses almost instantaneously, faster than light could traverse it. The mechanism for keeping a wormhole open is, once again, exotic matter with negative energy density. The Casimir effect provides the only currently known physical example, and the Casimir effect produces negative energy densities that are fantastically small, on the order of 10 to the minus 30 joules per cubic meter between plates separated by nanometers. Scaling this to the macroscopic amounts needed to stabilize a traversable wormhole would require Casimir plates covering an area many orders of magnitude larger than the observable universe. The second problem with wormholes is that they appear to require being constructed in the first place. Unlike natural stellar objects, stars, planets, black holes, that form spontaneously from gravitational collapse, wormholes have no known natural formation mechanism. Every proposed scenario for wormhole creation involves energy scales at or above the Planck scale, the regime where our current understanding of physics completely breaks down, and where quantum gravity effects dominate in ways we cannot currently describe. The third problem is causality. Kip Thorne and others have shown that traversable wormholes, if they existed and could be used for travel, would permit closed time-like curves, paths through spacetime that loop back on themselves, allowing an object to return to its own past. This produces logical paradoxes of the grandfather kills grandfather variety. Stephen Hawking's chronology protection conjecture suggests that quantum effects would prevent closed time-like curves from forming, effectively that the universe enforces its own causal structure against such violations. But this conjecture, while strongly motivated, is not proven. The fourth problem is that even if wormholes existed and were stable, and exotic matter were available to hold them open, their endpoints would need to be placed at both the origin and destination before they could be used for travel. How does one place an endpoint at a star 4 light-years away without first travelling there by conventional means. The wormhole solves the problem of getting from A to B only if you have already gotten one end of the wormhole to B. Wormholes are mathematically interesting objects in general relativity. They are not physical engineering options for interstellar travel. The third proposed mechanism deserves more careful treatment because it is more physically grounded than the previous two. This is the laser sail, specifically the concept behind Breakthrough Starshot. Breakthrough Starshot is a privately funded research initiative announced in 2016 by physicist Stephen Hawking and venture capitalist Yuri Milner, with initial funding of $100 million. Its goal is to develop a proof of concept for sending a gram-scale spacecraft to Alpha Centauri at 20% of the speed of light, arriving within roughly 20 years of launch.
The concept: a large array of ground-based or space-based lasers with combined power in the gigawatt to terawatt range illuminates an ultralight sail, a sheet of material perhaps a few meters across and a few hundred atoms thick, attached to a tiny payload. The radiation pressure of the laser beam accelerates the sail to a significant fraction of the speed of light over a period of minutes. Unlike rocket propulsion, the laser sail does not carry propellant. The energy source remains on Earth or in Earth orbit. The spacecraft can be made extraordinarily light, a gram or less for the sail and payload combined. The lower mass dramatically reduces the energy required compared to a conventional rocket. The physics is sound in principle. Radiation pressure is real. It is already used in a small way by solar sails in interplanetary missions. The challenge is one of scale and engineering difficulty. The laser array required to accelerate even a gram-scale sail to 20% of the speed of light must deliver roughly 100 gigawatts of coherent, directed laser power. This is approximately 10% of total United States electricity generating capacity, focused into a beam that must remain precisely pointed at a sail a few meters across that is receding at tens of thousands of kilometers per second. The pointing requirement is extraordinary. At the end of the acceleration phase, after the sail has traveled perhaps 10 million kilometers, the laser array must still be directing most of its energy onto the sail's reflective surface. Atmospheric turbulence, mirror imperfections, and diffraction all spread the beam. The array must be either in space or use adaptive optics of a sophistication far beyond current capabilities. The sail material must reflect virtually all incident laser energy.
If it absorbs even a fraction of a percent, the heating at 100 gigawatts input would vaporize any known material. Current best candidates include graphene sheets and silicon nitride membranes, materials that can be made atomically thin and have excellent optical properties. But fabricating them at the required scale and ensuring structural integrity during the acceleration pulse has not been demonstrated. The gram-scale payload, carrying cameras, communication systems, power generation and sensors, must fit within the limits of current or near-future nanotechnology. A functional scientific instrument at gram scale is not beyond imagination, but the miniaturization required is at or beyond the current frontier. And the communication problem: after 20 years of travel, the spacecraft is 4 light-years from Earth. Its transmitter must be powerful enough to return data across that distance.
A gram-scale transmitter with gram-scale power generation will produce a signal that, even with the largest receiving arrays on Earth, will be extraordinarily faint. Signal detection at interstellar distances from a milliwatt-class transmitter has not been demonstrated. Breakthrough Starshot has a further fundamental limitation that distinguishes it from any proposal that might apply to the problem of interstellar travel by human beings. The spacecraft has no deceleration mechanism. It arrives at Alpha Centauri at 20% of light speed and passes through the system in a matter of hours, conducting flyby observations before disappearing into the galaxy's far side. There is no way to stop it. A human crew cannot make a flyby visit to another star. They must decelerate at the destination, orbit, land if a habitable world exists, and eventually decelerate again at Earth on return.
Every component of this requires carrying propellant and energy for deceleration, which multiplies the mass budget by enormous factors. Breakthrough Starshot, if it succeeds, will be a genuine scientific triumph. It will demonstrate that interstellar transit is physically achievable, but it does not point toward human interstellar travel in any straightforward way. The physics of gram-scale probe travel and the physics of 1,000-ton crewed spacecraft are separated by 11 orders of magnitude in mass, and the rocket equation means that separation translates into an energy difference of far more than 11 orders of magnitude. Now let us think about what the barriers actually look like when taken together, because they compound, and their compounding produces something more severe than each individually. Imagine an engineering team tasked with designing the most advanced conceivable human interstellar spacecraft. No budget limits, access to physics at the frontier of current understanding, projected forward 1 or 2 centuries. What can they actually build? They need to get 1,000 tons to Proxima Centauri in a meaningful time frame, let us say 100 years, which requires roughly 4% of the speed of light. At 4% of the speed of light, the kinetic energy of the 1,000-ton spacecraft is approximately 7.2 times 10 to the 19th power joules. Manageable. Roughly equivalent to 12% of global annual energy consumption. The Lorentz factor at this speed is approximately 1.0008, so relativistic effects are negligible. No extreme time dilation, no extreme blue shifting of the cosmic microwave background. Good so far. But the propulsion system. What is the best propulsion system physics permits for this speed? Nuclear pulse propulsion, the Orion concept from the late 1950s, involves detonating a sequence of nuclear devices behind the spacecraft and absorbing the blast with a pusher plate. It is physically crude but energetically effective. Specific impulse can reach several thousand seconds for fission devices and potentially much higher for fusion devices. This is the most realistic near-term technology for achieving a few % of light speed. For a 1,000-ton spacecraft accelerated to 4% of light speed with nuclear pulse propulsion at, say, an effective exhaust velocity of 3% of light speed, the rocket equation gives a mass ratio of approximately e to the power of 0.04 over 0.03, approximately equals e to the power of 1.33, approximately equals 3.8. For every ton of spacecraft, roughly 2.8 tons of propellant. So the total launch mass is approximately 3,800 tons. 1,000 tons of spacecraft plus 2,800 tons of propellant. That propellant for a fusion pulse drive might be deuterium-helium-3 fuel. Obtaining 2,800 tons of helium-3 is itself a massive challenge. The entire Earth's atmosphere contains only a few thousand tons of helium-3, most of it impractically diffuse. And this is one way. For deceleration at the destination, the spacecraft must either carry additional propellant or use some external mechanism. If it carries deceleration propellant, the mass ratio compounds. If it uses a magnetic sail to decelerate against the interstellar medium at the destination, this imposes its own constraints on the sail size and the density of interstellar material, which is low enough that deceleration by this mechanism alone takes an extremely long time. The 1,000-ton spacecraft that arrives at Proxima Centauri is not the same 1,000 tons that left. Over 100 years of transit, or even 40 years at 10% of light speed, the spacecraft must maintain itself with minimal external support. Every component that fails must be repaired or replaced from onboard materials. Every consumable used by the crew must be resupplied from onboard stores or regenerated from waste. The life support requirements for 100 years are fundamentally different from the life support requirements for 6 months on the International Space Station. On the station, consumables are regularly resupplied. Systems that fail can be replaced with components from Earth. Medical emergencies can be addressed by returning the crew. None of these options exist for an interstellar crew. The spacecraft must be a completely self-contained civilization. It must grow food, which requires controlled agriculture systems with high reliability over decades. It must recycle water and air with efficiencies approaching 100%. Current station technology achieves 90 to 95% water recovery, which means significant losses over 100 years. It must maintain crew health without access to the global medical infrastructure that makes modern medicine effective. No specialist physicians from other institutions, no replacement medications that run out, no diagnostic equipment that can be shipped from Earth. The crew itself is a source of engineering constraints. A minimum viable crew for a multi-generational mission, a mission where the arriving population is descendants of the departing population, has been estimated at between 150 and several thousand people, depending on assumptions about genetic diversity management, skill preservation, and psychological stability. Lower estimates assume sophisticated genetic management technology, careful selection for psychological compatibility, and robust institutional mechanisms for preserving essential technical knowledge across generations. Each additional crew member increases the life support requirement, the food production requirement, and the total spacecraft mass. Every increase in spacecraft mass increases the propellant requirement. Every increase in propellant requirement increases the launch mass. The cascade is relentless. There is another constraint that is rarely discussed in popular treatments, but that may be the most severe of all for multi-generational missions: knowledge preservation. A technical civilization requires specialists. A spacecraft capable of sustaining human life at interstellar distances requires nuclear engineers, atmospheric chemists, geneticists, agricultural specialists, physicians, structural engineers, computer scientists, and dozens of other highly trained disciplines. Maintaining each specialty requires not just individual expertise, but educational infrastructure, the ability to train the next generation. On Earth, this works because the total population is large enough to support deep specialization, and because knowledge is distributed across billions of individuals and countless institutions. If one expert dies, others exist. If one institution's records are lost, other institutions preserve copies. On a spacecraft with a few hundred to a few thousand people, knowledge concentration is an existential risk. If the chief nuclear engineer dies without fully training a successor, the reactor becomes a black box. If the atmospheric management specialist's knowledge is not preserved in sufficient detail, a cascade failure in the life support system becomes undiagnosable. Civilizations on Earth have lost critical technical knowledge: the Roman recipe for concrete, ancient navigation techniques, medieval cathedral construction methods, and survived because they had the resources of a planet to fall back on. An interstellar spacecraft has only itself. The management of knowledge across generations, ensuring that the expertise necessary to maintain a complex technological system is preserved and transmitted without degradation over decades or centuries, is a problem without historical precedent at the scale required. No human institution has successfully maintained technical expertise in total isolation for even a century, let alone the multi-generational timescales that slower interstellar missions require. Now let us think carefully about the second physical wall, the one that applies not just to travel through space, but to any attempt to communicate faster than light. The speed of light is not just a limit on physical travel. It is a limit on the propagation of any physical influence, any transfer of matter, energy, or information. No signal of any kind can travel faster than light through empty space. This is not a consequence of the specific properties of electromagnetic radiation. It is a fundamental feature of the causal structure of spacetime. This means that an interstellar civilization, even one that has managed to move people between stars, faces a communication delay that cannot be reduced below the light travel time. A message from Proxima Centauri to Earth takes 4.24 years. A response returns 4.24 years later. The minimum round-trip communication time is 8.48 years. This has profound implications for any interstellar civilization. A centralized government cannot govern interstellar colonies in real time. Economic coordination across light years requires strategies fundamentally different from anything that works within a single solar system. A civilization at Alpha Centauri and a civilization at Earth are, in a meaningful sense, incommunicado, able to exchange messages but not to interact, not to coordinate in real time, not to form the kind of integrated social and economic fabric that binds continents together on Earth. Each interstellar outpost is necessarily autonomous. It must be capable of making all critical decisions without consulting its origin civilization. It must be self-sufficient in all essential resources. It must develop its own governance, its own culture, its own identity. The communication delay is not a technical problem that better technology will solve. It is built into the causal structure of space-time by the same physics that makes faster-than-light travel impossible. Any civilization attempting to span multiple star systems must grapple with the reality that its components will diverge, culturally, politically, biologically, in proportion to the communication delays separating them. This is one reason why the idea of a galactic empire, a single political entity spanning many star systems, is physically implausible regardless of the technology available. The governance latency makes it impossible. By the time a command reaches a colony 100 light-years away and a response returns, 200 years have elapsed. The command is responding to a situation that no longer exists. The response is coming from a civilization that has had 2 centuries to develop its own character. Now let us look at what physics actually allows, stripped of all wishful thinking, for interstellar travel within timescales meaningful to human civilization. The physically honest answer involves a spectrum. At one extreme, robotic probes. A gram-scale laser sail of the breakthrough starshot type is physically achievable with technology that is 2 to 3 generations of engineering ahead of current capabilities. It cannot carry humans. It cannot decelerate at the destination. It offers a few hours of flyby data collection at the target system before continuing out of the galaxy. But it represents a physically achievable first step. The ability to send instruments, if not people, to another star within a time frame shorter than a human lifetime. Further along, autonomous robotic missions with deceleration capability. A larger spacecraft, perhaps tens of tons rather than grams, with onboard propulsion for deceleration, could conduct proper scientific investigations of a target star system. It would need to carry far more propellant and would require far more energy to accelerate. Decades of travel time at a few % of light speed. The information returned would take additional years to arrive at Earth. Total round-trip information time, perhaps a century. Achievable in principle by a civilization with nuclear fusion propulsion technology and the organizational commitment to sustain a century-long project. Further still, crewed missions. The smallest conceivably viable crewed mission to the nearest star, assuming nuclear fusion propulsion, extensive life support technology beyond current capabilities, and a minimum viable crew of perhaps 150 to 200 people, would require a total spacecraft mass in the range of tens of thousands to hundreds of thousands of tons at launch. The energy to accelerate this mass to 5 to 10% of the speed of light is on the order of planetary energy budgets. The mission duration is multiple decades for the crew. The mission requires that arriving crew members found a self-sufficient colony because the return journey is not practically achievable for the same individuals. The aging, radiation exposure, and physical deconditioning accumulated over decades of travel make the prospect of a return journey progressively less viable with every additional year at the destination. This is the physical reality. It is not a failure of imagination. It is an accurate accounting of what physics permits and what it prohibits, and where on the spectrum between permitted and prohibited current and near-future technology actually falls. The wall the universe built is not a single barrier. It is a layered system of constraints: energy, propellant mass, radiation, interstellar medium, time, human biology, knowledge preservation, communication delay. Each individually challenging, all simultaneously operating, each constraint interacting with the others in ways that compound rather than cancel. Any civilization anywhere in the universe attempting interstellar travel faces this same system of constraints. The specific technological implementations available to them may differ enormously from ours. Their energy generation capacity may dwarf ours. Their materials science may be centuries beyond our current frontier. Their spacecraft engineering may be capable of things we cannot imagine, but the physical laws are the same. Momentum must be conserved. Energy cannot be created from nothing. The speed of light is an absolute limit in flat spacetime. Radiation damages biological systems. Mass requires energy to accelerate. Communication cannot exceed the speed of light. These are not engineering limits, they are the structural properties of the universe. This is why the Fermi paradox carries such weight. If interstellar travel is this difficult, if even the most advanced possible civilizations face these constraints, then the silence of the universe becomes less surprising and more revelatory. Not because interstellar travel is impossible, it is not. Physics allows it. Because physics makes it so expensive, so slow, so demanding of resources and commitment, that it may be the exception rather than the rule, even for civilizations that have had billions of years to develop. The galaxy is not silent because no one exists. It may be silent because crossing the distances between stars is genuinely, physically, irreducibly hard. Hard enough that most civilizations that develop the ability to detect the universe's scale also develop the understanding that crossing it is beyond what any finite civilization can readily sustain. That is the wall the universe built. Not to punish curiosity, not to imprison life, but as a simple consequence of the laws that make atoms stable, stars luminous, and galaxies possible. The same physics that created the stars also placed them beyond easy reach. And understanding that, really understanding it, numbers and all, changes what it means to look up at the night sky. Let us now think carefully about what the wall actually looks like from the inside, from the perspective of a civilization that has genuinely grappled with these constraints and made rational decisions about how to respond to them. Because the barriers to interstellar travel are not just physical facts that exist in textbooks. They are facts that any technologically advanced civilization will eventually confront and will have to decide how to respond to. The decisions they make, and the decisions we will eventually have to make, reveal something important about what kind of species we are and what the universe's structure demands of intelligence. Start with the energy problem, examined from the perspective of what it would actually take to build an interstellar civilization. A civilization capable of sustained interstellar travel, not one-off missions but regular departures, the establishment of multiple colonies, the maintenance of at least minimal communication and coordination across light years, needs to be what Nikolai Kardashev described as a Type II civilization on his scale. A Type II civilization harvests the full energy output of its host star. The Sun radiates approximately 3.8 times 10 to the 26th power watts. This is the energy source that Type II technology would access. Compare this to current human energy consumption, roughly 6 times 10 to the 13th power watts.
The gap between where we are and Type 2 is a factor of roughly 6 trillion. How do you close a factor of 6 trillion? Not by building more coal plants, not by covering a continent with solar panels. The scale of the gap requires restructuring the civilization's relationship to its energy source at the most fundamental level. The theoretical mechanism is the Dyson sphere, or more realistically, a Dyson swarm. A collection of structures orbiting the star at various radii, each collecting solar energy and transmitting it to wherever it is needed. No known physical law prohibits this. The materials exist in the solar system in sufficient quantity, primarily in asteroids and the outer planet moons. The engineering challenges are enormous, but are problems of organizational scale, not fundamental physics. Freeman Dyson's original 1960 paper estimated that a civilization developing at a reasonable rate could complete such a structure in a few thousand years, using the materials available in a typical solar system. This seems fantastically ambitious, until you compare it to what humanity has accomplished in the few thousand years since the invention of writing. We went from stone tools to a global industrial civilization with nuclear weapons in roughly 10,000 years. The Dyson swarm is a larger project, but it is not obviously more ambitious in proportion to the technological base required to begin it. The significant point is this: a civilization capable of sustained interstellar travel has, by necessity, already accomplished something comparable to the Dyson swarm. The energy requirements cannot be met any other way. This means that any civilization sending crewed ships to other stars is already operating at a scale of engineering that makes the entire surface area of its home planet look like a footnote. From this perspective, the barrier to interstellar travel is not just physics, it is civilization scale. It requires the prior achievement of a level of resource mobilization that dwarfs anything in human history by many orders of magnitude. And here is a crucial implication. A civilization that has achieved this scale is not desperate. It is not motivated by resource scarcity at home. It has harnessed its star. It is not threatened by any internal catastrophe that would require immediate relocation to another star system. It has the engineering capability to address internal problems at a scale we cannot conceive. The motivation for interstellar travel at that level of capability must be something other than survival necessity. It must be curiosity, the desire to explore, the drive to expand the presence of the civilization beyond a single star system for its own sake, cultural, philosophical, scientific. This matters for thinking about why we do not see evidence of such civilizations in our galaxy. If the motivation is purely voluntary, if survival does not demand it, then many civilizations may simply choose not to. The cost is real and enormous, even for a Type 2 civilization. The benefit, contact with distant star systems across timescales of decades and centuries, may not justify that cost from within the framework of values that a long-lived, stable, resource-rich civilization develops. This is one resolution to the Fermi paradox that does not require catastrophe. Advanced civilizations exist, but are not aggressively expanding, because expansion is expensive, slow, and not urgently necessary. Now let us think about what happens to the physics of interstellar travel as we push into the genuinely exotic. Not engineering solutions, but theoretical structures in physics that are taken seriously by working scientists, however speculative. Quantum mechanics at the macroscopic level has an important consequence for the structure of spacetime. General relativity, which governs the large-scale structure of the universe, treats spacetime as a smooth, continuous manifold. a geometric object that curves in response to mass and energy. Quantum mechanics governs the small-scale behavior of matter and energy, and at quantum scales, fields fluctuate. Space is not smooth and quiet, but seething with vacuum energy, virtual particle pairs appearing and disappearing, quantum foam. At the Planck scale, roughly 10 to the minus 35 meters, these quantum fluctuations become so intense that the usual geometric description of spacetime breaks down completely. General relativity fails. Quantum mechanics, as usually formulated, also fails. We need a theory of quantum gravity to describe what happens at this scale, and we do not currently have one. String theory and loop quantum gravity are the two leading candidates, but neither has produced testable predictions that distinguish it from alternatives, and neither is empirically confirmed. The quantum structure of spacetime at the Planck scale remains one of the deepest open questions in theoretical physics. Why does this matter for interstellar travel? Because some theoretical physicists believe that the resolution of the tension between general relativity and quantum mechanics may reveal new features of spacetime that we do not currently understand, features that could, in principle, permit forms of travel or communication that appear impossible within current theory. This is not wishful thinking layered onto ignorance. It is an observation that our current theoretical framework is demonstrably incomplete. It contains internal contradictions at extreme scales, and that the resolution of those contradictions might change the picture. One specific example, the holographic principle. The holographic principle, arising from work by Gerard de Hooft, Jacob Bekenstein, Stephen Hawking, and Leonard Susskind on the physics of black holes, suggests that the information content of a region of space is proportional to the surface area surrounding it, rather than the volume. In some formulations, this implies that a three-dimensional volume of space is, in some deep sense, encoded in a two-dimensional surface, that the universe may have a fundamentally different structure than the three-dimensional space we experience. The ADS/CFT correspondence, a mathematical duality worked out in string theory, provides a specific technical realization of this idea, showing that certain quantum gravity theories in a particular geometry are exactly equivalent to quantum field theories on the boundary of that geometry. This is not merely a mathematical curiosity. It has been used to make precise calculations in strongly coupled quantum systems that are directly tested in experiments. If the universe has this kind of non-local structure at a fundamental level, if the physical content of a three-dimensional region is genuinely encoded in its boundary, then our understanding of locality itself may need revision. The statement that 2 points in space are separated by 4 light years may be accurate as a description of the emergent, low-energy geometric structure we experience, while being misleading about the deeper structure of reality. This does not obviously help with interstellar travel. It does not provide a mechanism for moving mass or information faster than light. But it suggests that our current picture of what space actually is, and therefore what it means to cross it, may be importantly incomplete. The same applies to the measurement problem in quantum mechanics. When a quantum system interacts with a measuring apparatus, the apparent randomness of the outcome and the apparent collapse of the quantum state to a definite value has resisted satisfactory explanation for nearly a century. The many worlds interpretation, the Copenhagen interpretation, decoherence-based approaches, and various collapse models all make the same empirical predictions for experiments we can currently conduct, which means we cannot distinguish between them experimentally. But the different interpretations have different implications for the structure of reality. The many worlds interpretation, taken seriously, implies that every quantum measurement outcome is realized in some branch of a branching multiverse. The implications of this, if true, for what it means to travel between 2 points in space, when those points exist in an enormous branching structure of parallel realities, are genuinely unclear. These are not arguments that faster-than-light travel is possible. They are arguments that our current understanding of physics is demonstrably incomplete at fundamental levels, and that the completion of that understanding might change the picture in ways we cannot fully anticipate. In 1900, the physicist Lord Kelvin reportedly said that physics was essentially complete. Only two small clouds remained on the horizon of understanding. Those two small clouds turned out to be quantum mechanics and relativity, which between them overturned the entire framework of physics from Newton onward. We are not in 1900.
We know our current framework is incomplete. We know exactly where the seams are, at the Planck scale, at the intersection of quantum mechanics and gravity, in the measurement problem, in the foundations of statistical mechanics. We do not know what the resolution of these tensions will look like. We cannot rule out that it will produce surprises as radical as quantum mechanics and relativity were for Newtonian physics. This is genuine scientific humility, not wishful thinking. It is the acknowledgement that the phrase "impossible as far as we know" carries real epistemic weight, that what we know, while vast, is not complete. With that caveat clearly stated, let us return to what we do know and think about it with care. The barriers to interstellar travel are real. The energy requirements are enormous. The propellant problem is severe. The radiation environment at high velocity is hostile. The interstellar medium at high velocity is dangerous. Human biology is fragile in ways that become catastrophic on the timescales involved. Knowledge preservation across generations is a problem without solved analogues. The communication delay fundamentally limits the coherence of any civilization spanning multiple star systems. None of these barriers is individually insurmountable for a sufficiently advanced civilization. Each has, at least in principle, physical solutions. Solutions that require technology far beyond ours, but do not violate known physical law. The problem is that the solutions compound. Shielding the crew from radiation requires mass. Mass requires propellant. Propellant requires energy. Energy requires infrastructure. Infrastructure requires crew. Crew requires life support. Life support requires reliability. Reliability requires redundancy. Redundancy requires mass. The cascade continues. The wall the universe built is not a single obstacle. It is a system of mutually reinforcing constraints that makes every attempted solution more expensive than a naive analysis would suggest. This is why serious mission planning for interstellar travel, the kind done by physicists and engineers who have worked through all the numbers, consistently produces assessments that are far more sobering than science fiction suggests. The Project Daedalus study from the 1970s, the Project Icarus refinements begun in 2009, the Tau Zero Foundation's technical analyses, the peer-reviewed literature on nuclear pulse propulsion and laser sail concepts, all of these conclude that interstellar travel is physically possible, but demands resources and capabilities that are qualitatively beyond anything humanity currently possesses and will not achieve on any short timescale. Now let us think about what this means for the search for extraterrestrial intelligence, and specifically for interpreting the Fermi paradox in light of everything we have established. The Fermi paradox rests on a simple observation. The galaxy is old, life has had billions of years to develop, and if any civilization ever achieved the ability to expand across the galaxy, that expansion should have filled the galaxy many times over with detectable signatures by now. We observe none. Where is everybody? The standard resolutions cluster into a few categories. The first category, the barriers we have been discussing, are high enough that no civilization has overcome them. Life may be common, intelligence may be common, technological civilizations may be common,
But the leap from technological civilization to interstellar civilization may be so expensive and difficult that none have made it, or so few have made it that their signatures are below our detection threshold. This is the most physically grounded resolution. It does not require any exotic catastrophe. It requires only that the barriers we have been discussing are real, and that most civilizations, on honest cost-benefit analysis, decide that the investment is not worth it, or that they try and fail at the critical technical hurdles, or that their civilization does not persist long enough to accumulate the energy resources required. The second category: civilizations achieve interstellar capability but do not expand aggressively. The resource base available in a single solar system, properly developed, supports a civilization of enormous scale, potentially trillions of individuals, access to energies on stellar scales, computational resources that dwarf anything imaginable from our current vantage point. The motivation to undergo the enormous expense of interstellar colonization when home is so rich may simply not develop. This is the zoo hypothesis, or the sustainability hypothesis, or various other named variants. Civilizations look out at the interstellar distances, do the math, and decide to develop inward rather than outward. They build virtual realities, explore the mathematics of their universe, develop art and culture to levels we cannot imagine, without ever launching a single colony ship. From the outside, this would look indistinguishable from the first resolution. We would see silence either way. The third category: civilizations expand, but their signatures are not what we are looking for. A galaxy-spanning civilization might use communication channels we have not thought to monitor: neutrinos, gravitational waves, exotic quantum states. It might use energy with such efficiency that it leaves no thermodynamic waste signature. It might deliberately conceal its presence for reasons we cannot guess. This requires something of a conspiracy of silence across many independent civilizations. They all need to be hiding, or they all need to independently choose communication modes we haven't looked at. The more civilizations exist, the less plausible universal concealment becomes. The fourth category: the great filter. Something typically ends civilizations before they reach interstellar capability. It might be in the past. The development of life, or complex life, or intelligence was so improbable that we are alone, or nearly so. It might be in the future. Something tends to destroy technological civilizations before they achieve interstellar status. Nuclear weapons, engineered pandemics, misaligned artificial intelligence, climate collapse, resource exhaustion, internal social fragmentation. Any of these could represent a characteristic barrier that civilizations typically fail to cross. The silence of the universe is then explained by the rarity of those that survive. The Fermi paradox does not have a confirmed resolution, but the physical barriers to interstellar travel, clearly understood, make the first two resolutions substantially more plausible than they seemed before examining the constraints carefully. If interstellar travel is genuinely enormously difficult, if it requires resources that take civilizations millions of years to accumulate, sustained commitment across timescales that challenge any known social institution, and tolerance for risks that are not fully manageable, then the absence of widespread galactic colonization does not require catastrophe. It requires only that the physics is as hard as it actually is. Now let us think about something that rarely enters these discussions, but that changes the nature of the problem in an important way: the role of automation and artificial intelligence in interstellar travel. Human beings are, as we have established, fragile. They require a specific atmosphere at a specific pressure.
They require food and water. They are damaged by radiation. Their psychology deteriorates in isolation over long periods. Their biology adapts in ways that may make them non-functional in their destination environment after long transit times. An artificial intelligence, or a sophisticated robotic system, has none of these requirements in their biological form. It does not need oxygen. It does not need food. It does not age in a radiation environment in the same catastrophic way biological cells do. It does not become psychologically unstable after years of isolation. The information content of a human mind, the memories, knowledge, values, and personality patterns that define an individual, is encoded in the approximately 86 billion neurons and their roughly 100 trillion synaptic connections. Current estimates suggest this information content is roughly on the order of 2.5 petabytes. That is a large number by current computing standards, but is not beyond scaling extrapolation of current trends. If mind uploading, the transfer of a human mind's information content to a digital substrate, is achievable in principle, then interstellar travel changes character. A digital mind travelling at 10% of the speed of light in a small, robust, well-shielded spacecraft could make the journey to Proxima Centauri in 42 years. It would not age during transit. It would not be damaged by radiation in the way biological cells are. Radiation-hardened electronics are robust to the environments involved. It would not need to eat, breathe, or maintain a complex life support ecosystem. At the destination, it could be instantiated in a robotic body or transmitted back to Earth as a data signal, also at the speed of light, while its hardware remains at the destination. The obstacles are deep. The hard problem of consciousness, whether information processing of sufficient complexity produces subjective experience, and whether a digital copy of a brain is the same person as the biological original, is not resolved and may not be resolvable with any scientific technique. The ethics of creating and ending digital minds, of transmitting copies, of what rights such entities have, are not worked out. But as a physical matter, mind uploading does not obviously violate any known physical law. It is a different category of impossibility from faster-than-light travel. It is not prohibited in the way that exceeding the speed of light is prohibited. It may be practically impossible, or philosophically incoherent, or ethical disaster, but it is not physically ruled out. If it is achievable, interstellar travel becomes a fundamentally different proposition. The bottleneck shifts from getting biological humans across the void to getting robust digital minds and their physical substrate across the void, or to transmitting information at the speed of light and instantiating it at the destination. Information transmission is already happening at the speed of light. We do it every time we send a radio signal. The question is whether the information being transmitted at light speed can be used to reconstruct a human being at the destination. The answer to that question depends on physics we do not yet understand, and philosophy that may not have a clean answer. This is perhaps the most genuinely interesting frontier in thinking about interstellar travel. Not the propulsion problem, not the shielding problem, but the question of whether the relevant thing to move between stars is mass or information. Now let us think carefully about a specific physical proposal that has received serious attention from working physicists and that represents the most physically grounded near-term approach to interstellar communication, if not travel. This is the solar gravitational lens. General relativity predicts that mass curves spacetime, and that light traveling near a massive object follows the curvature of spacetime, bending its path. This gravitational lensing effect has been observed directly. It explains the distorted images of galaxies behind massive galaxy clusters, and it was the basis for the famous 1919 eclipse expedition that confirmed general relativity. The Sun's gravitational field focuses light from distant sources into a focal region that begins approximately 550 astronomical units from the Sun, roughly 550 times the Earth-Sun distance,
or about 82 billion kilometers from the Sun.
The focal region extends outward from this point. Sources at different distances from our Sun come to focus at different points along the focal axis. A telescope placed in the focal region of the solar gravitational lens would have its effective aperture amplified enormously, by a factor of roughly 100 billion compared to a conventional telescope at the same position. This amplification would allow imaging of objects with extraordinary resolution and sensitivity at interstellar distances. Physicist Claudio Marcone has worked out the details. A spacecraft at the solar gravitational lens focus could, in principle, image the surface of a planet orbiting another star at resolutions of tens of kilometers, enough to see continental features, potentially to detect city-scale structures if they existed. The challenge is getting to 550 astronomical units. The fastest spacecraft humanity has ever launched, New Horizons, took about 9 years to reach Pluto at roughly 35 astronomical units. Reaching 550 astronomical units at the same speed would take roughly 140 years. With near-future advanced propulsion, nuclear electric or nuclear thermal, the travel time might be reduced to a few decades. This is not interstellar travel, but it is a physically achievable means of gathering enormous amounts of information about other star systems without crossing the interstellar void, a complement to and partial substitute for physical visits. If a civilization discovered a habitable planet at another star through solar gravitational lens observations, the information returned would be detailed enough to plan a targeted mission, or to decide that no mission is warranted. The combination of extremely detailed remote sensing with targeted robotic probes represents a path to understanding other star systems that is far more physically tractable than the full interstellar crewed mission. This is likely how any serious interstellar civilization would actually proceed, not by launching crewed ships blindly into the void toward targets of unknown character, but by first gathering detailed information remotely, then sending robotic scouts, then, if the destination justifies it, considering a crewed follow-up. Now let us pull back and think about what the totality of this analysis tells us about the place of intelligence in the universe. The universe is approximately 13.8 billion years old. Our solar system formed about 4.6 billion years ago. Life appeared on Earth roughly 3.8 billion years ago. Complex multicellular life appeared roughly 600 million years ago. Homo sapiens appeared roughly 300,000 years ago. We developed agriculture about 10,000 years ago. We discovered physics as a systematic discipline about 400 years ago. We reached the moon about 55 years ago. On the cosmic scale, we are extraordinarily new. Our technological civilization is a geological eye blink, an instant in the 13.8 billion year history of the universe. Other civilizations, if they exist, have had vastly more time. Stars older than our Sun by 1 billion years exist in our galaxy. A civilization that appeared around such a star and developed technology on a timeline comparable to ours would have had 1 billion more years of development than we have. The gap between where we are and where a billion-year-old technological civilization might be is difficult to even frame conceptually. And yet, we see no evidence of such a civilization. No megastructures, no galaxy-spanning networks of relay stations, no engineered stellar objects, no signatures of energy use on the scales we would expect from a civilization that has had 1 billion years to develop its resource base. This absence is data. It tells us something. It tells us either that such civilizations do not exist, that we are early or alone, or that the step from biological life to lasting technological civilization is so rare that we are among the first, or that such civilizations do not leave the kinds of signatures we expect, that the physics of interstellar expansion is harder than we imagine, even for billion-year-old civilizations, or that the motivations we expect are absent, or that the signatures are there and we are simply not looking in the right way.
The physical barriers to interstellar travel, taken seriously, contribute to explaining the absence. If even a billion-year-old civilization finds interstellar expansion genuinely expensive, if the energy costs are real, if the distances remain real, if time and mass and physics cannot be circumvented, then the silence of the universe becomes less surprising. The universe built a barrier.
It built it carefully into the structure of space-time itself, into the conservation laws, into the relationship between mass and energy, into the geometry of the cosmos. The barrier does not prevent interstellar travel. Nothing physical prohibits it. But the barrier ensures that it is never easy, never cheap, and never the path of least resistance for any civilization that has not first demonstrated commitment to civilization-scale engineering over geological timescales. That is not a wall designed to imprison life. It is a feature of a universe that obeys consistent mathematical laws, laws that happen in their consistency to make the stars difficult to reach. Whether intelligence, in its determination and curiosity, eventually overcomes that difficulty, here or around other stars, is a question that physics alone cannot answer. Physics only defines the terms.
Let us now think about something that the previous analysis has circled without landing on directly. The question of what interstellar travel actually demands of a civilization. Not in terms of physics or engineering, but in terms of values, institutions, and the kind of long-term thinking that no human civilization has ever sustained. Because the physical barriers, real as they are, may not be the binding constraint. The binding constraint may be something more fundamental. The difficulty of organizing and sustaining a civilization-scale project across timescales that exceed the lifespan of any institution, any government, any culture, any individual human motivation. Consider the timeline. The most optimistic, realistic scenario for a crewed interstellar mission, using technology that is plausibly achievable within a few centuries, using nuclear fusion propulsion targeting the nearest star, involves a mission development phase of perhaps a century, a transit time of 40 to 100 years, and an arrival at a destination that requires immediate establishment of a self-sufficient colony, because return is not practical for the initial crew. From first commitment to first human footstep on an exoplanet, 140 to 200 years minimum. More likely 300 to 500 years if you include the energy infrastructure development required before mission launch becomes feasible. What human institution has sustained a single project for 300 years? The Catholic Church has existed for nearly 2,000 years, but it has undergone schisms, reforms, corruptions, and transformations that make it unrecognizable compared to its early form.
It has sustained certain ideas, certain practices, certain organizational structures, but not a specific technical project. Some cathedrals took 200 to 400 years to build. Cologne Cathedral, begun in 1248, was not completed until 1880, 632 years. But cathedral construction was never a single continuous project, requiring unbroken chain of command and institutional continuity. It was a series of successive generations taking up a shared cultural commitment, with interruptions, restarts, and changes of direction. No government currently existing has sustained a continuous institutional identity for 300 years, with the kind of consistent technical commitment that an interstellar mission would require. The United States is 250 years old and has already seen dramatic changes in its political character, its institutional structures, and its technical capabilities. The Chinese state claims a longer, continuous history, but the specific institutional arrangements and values have changed radically across those centuries. A 300-year interstellar project would span multiple political systems, multiple technological revolutions, multiple cultural upheavals. It would require each successive administration, whatever form that takes,
to maintain commitment to a project that will not see results within any living person's memory of decision. The first decision makers will be dead before the spacecraft is launched. The launch crew will be dead before the spacecraft arrives. The arriving colonists will be descendants who had no direct say in the commitment their ancestors made. This is the generational commitment problem, and it is distinct from and arguably more severe than any of the engineering problems. Human psychology is not well suited to this. Our motivational systems evolved to respond to near-term rewards and near-term threats.
We discount future benefits relative to present ones, systematically, predictably, and in ways that are difficult to override even when we understand them. We struggle to maintain commitment to projects whose payoffs are decades away, let alone centuries. The exceptions are instructive. Religious institutions have sometimes sustained commitments across centuries because religion provides a motivational framework that transcends individual lifespans and connects present action to cosmic significance. National identity can sustain long-term commitments. Nations have built infrastructure that takes generations to complete, maintained military commitments across decades, sustained scientific programs across political transitions. Scientific communities have maintained research traditions across centuries through the mechanisms of publication, replication, education, and professional identity. An interstellar program would need to draw on all of these: the motivational depth of religion, the organizational continuity of the state, and the intellectual coherence of a scientific discipline, simultaneously, and sustain all three for longer than any of them has individually been sustained in human history. This is not obviously impossible. It is obviously unprecedented. And the precedent problem matters in an interesting way for thinking about extraterrestrial civilizations. If the binding constraint on interstellar expansion is not physics, but the difficulty of sustaining multi-century institutional commitments, then civilizations that achieve interstellar travel are not necessarily those with the best engineering. They are those that developed the right cultural and institutional structures for sustaining very long projects. Those structures might look very different from anything in human history. They might involve forms of governance we have not invented, value systems that prioritize the very long term in ways that are alien to any existing human culture, or, perhaps most intriguingly, biological or cognitive modifications that change the relationship between intelligence and time. A being that lives for 1,000 years, or that experiences time differently from biological humans, or that maintains continuity of identity across centuries through some substrate not dependent on fragile biological tissue. Such a being would have a fundamentally different relationship to a 300-year project than any current human does. This connects to something important about the trajectory of intelligence in the universe. Biological intelligence is a substrate that evolution found useful on at least one planet. It is capable enough to develop technology and eventually understand its own nature. But it may not be the final form that intelligence takes, in the same way that single-celled organisms were not the final form that life took. The development of artificial intelligence, systems that can process information and reason about the world without the biological substrate, represents the possibility of a different kind of mind, one not subject to the constraints of evolution, not limited to human-scale timescales, not dependent on the fragile biochemistry that makes biological brains vulnerable to radiation and aging and psychological deterioration. If artificial intelligence continues to develop, and there is no physical reason it should not, then the minds that eventually grapple with the interstellar travel problem may be minds that maintain continuity across centuries without difficulty, that do not experience the psychological deterioration of long isolation, that can run slower or faster depending on available energy, that can be copied and transmitted and reconstructed across the void as information rather than mass. This changes the nature of the problem in ways that are difficult to fully think through from inside a biological human perspective. But let us try. If the relevant agent for interstellar travel is not a biological crew, but a digital mind, or a swarm of digital minds running on radiation-hardened computing substrate, then many of the constraints we have been discussing are relaxed. Life support requirements drop dramatically. There is no need for food production, air recycling, or medical care for biological bodies. The mass budget for a crewed mission is dominated by the life support systems. For a purely digital crew, these components are eliminated. The radiation problem changes character. Biological cells are vulnerable to radiation because radiation damages DNA and disrupts the complex biochemistry of living cells in ways that are difficult to repair. Digital computing substrate is also susceptible to radiation damage, but the failure modes are different and more controllable. Radiation-hardened electronics have been used in extreme environments: nuclear power plants, space probes in the radiation belts of Jupiter. The damage is quantifiable, predictable, and can be managed through redundancy and error correction in ways that biological damage cannot. The psychological problem disappears. A digital mind does not experience isolation in the way a biological human does. It does not have a circadian rhythm disrupted by artificial lighting. It does not have a social drive that requires continuous contact with others. It does not experience the kind of existential dread that a human feels contemplating permanent separation from their home world. The time horizon problem shifts. A digital mind can be run at lower fidelity during transit, at reduced clock speed, using less energy, and brought to full capability at the destination. The transit of 42 years is not experienced as 42 years of subjective isolation. It is experienced as a much shorter period, or as no experience at all if the system is effectively suspended during transit. The knowledge preservation problem becomes more tractable. Digital information can be copied with perfect fidelity, stored redundantly, and verified for corruption in ways that biological memory cannot be. The technical knowledge required to operate the spacecraft and establish the colony can be preserved across the transit without relying on the imperfect transmission mechanisms of education and culture. The generational commitment problem might dissolve entirely. A digital mind that commits to an interstellar mission in 2100 can still be executing that commitment in 2400. Not through institutional continuity or cultural transmission, but through literal personal continuity. The same mind, in the same form, carrying out the same mission across 3 centuries. These advantages are real. They do not come for free. They assume a level of artificial intelligence and mind-uploading technology that does not currently exist, but they are not physically prohibited. They represent a path to interstellar travel that is qualitatively different from the path available to biological humans. And they suggest that if interstellar travel is ever achieved, it may be achieved by minds that are no longer biological in the way we currently are. This is uncomfortable to contemplate from a human-centered perspective. It implies that the beings who first walk on the surface of a planet around another star may not be human in the sense we mean today, that they may be descendants of humanity in a philosophical or historical sense, but not in the biological sense. It raises questions about identity, continuity, and what it means to be human that do not have settled answers in any existing philosophical tradition. But it is consistent with the physics. The physics cares nothing about the substrate of the mind. It cares about mass, energy, velocity, and time. If intelligence can find a substrate that reduces mass, tolerates radiation, and does not require biological life support, the physics becomes substantially more tractable. Now let us think about the information-centric view of interstellar travel in more depth, because it represents perhaps the most important shift in how to think about the problem. In the conventional framing, interstellar travel is about moving mass from one star system to another. The mass includes the spacecraft structure, the propulsion system, the life support, the crew, the scientific instruments,
and all the consumables for the mission. The challenge is generating enough energy to accelerate this mass to an appropriate speed. In the information-centric framing, interstellar travel is about moving information from one star system to another, specifically the information required to reconstruct whatever is being sent. Mass is the carrier of that information, and it must physically traverse the distance. But if the information can be separated from the mass and transmitted at light speed, the problem changes fundamentally. Consider what is actually needed at the destination. A colony at another star needs people or their digital equivalents, knowledge, technology, genetic diversity, cultural heritage, and the means to build a self-sustaining civilization. Currently, all of these require physical transport. Humans with their biology, libraries in physical storage, tools and machinery. But consider each element separately. People. If mind uploading is possible, people can be transmitted as data at light speed. A human mind digitized on Earth can be transmitted to a receiver at Proxima Centauri in 4.24 years. At the destination, a robotic system, sent physically ahead of the transmission, can instantiate the digital mind in a new substrate. Knowledge, already transmissible as data. The entire scientific knowledge base of human civilization can be encoded and transmitted as radio or laser signals. The challenge is not transmission, but reception. A receiver must already exist at the destination. Genetic diversity. The human genome can be stored digitally and transmitted. At the destination, synthetic biology technology, also sent ahead physically, can use the transmitted genetic information to grow biological humans from scratch. Technology. The designs for any device can be transmitted as data. Manufacturing capability at the destination, itself initially sent physically, can produce the physical devices from local materials. Cultural heritage. Literature, art, music, film, the recorded output of human civilization, all of this is already in digital form and can be transmitted. In this framework, the physical payload that must make the actual journey is dramatically reduced. Instead of a crude spacecraft with life support for 40 years, the physical payload is a small autonomous robotic system, a seed, capable of setting up a receiver for subsequent data transmissions, establishing power generation from local resources, beginning to construct manufacturing infrastructure, ultimately using transmitted designs and genetic information to recreate a human presence. This seed could be much smaller and lighter than any crude spacecraft. It might be achievable with laser sail technology on the breakthrough Starshot model, a gram-scale or kilogram-scale probe that carries the initial seed of the robotic infrastructure. Subsequent, larger physical payloads could follow using conventional propulsion. The information-centric model does not eliminate the physical barriers. Something must still cross the void, but it dramatically reduces what must cross. Instead of thousands of tons of life support and crew, a kilogram of robotic seed plus light-speed data transmissions. The physics of the reduced mass is orders of magnitude more tractable. A kilogram sail at 20% of the speed of light requires megawatts of laser power for minutes, achievable in principle. A 1,000-ton crude spacecraft at 10% of the speed of light requires energy equivalent to years of global energy production. The gap is many orders of magnitude. The information-centric model exploits that gap by separating what must physically travel from what can travel as light. The deep assumptions this requires, mind uploading, advanced synthetic biology, sophisticated autonomous robotics, are not within current technological reach. But they are not physically prohibited. They are on trajectories that, if continued, could be reached within centuries rather than millennia. And they change the nature of the problem enough that interstellar civilization,
the establishment of a human or post-human presence at multiple star systems, shifts from the domain of the physically possible but practically absurd into the domain of the physically possible and, given sufficient time and technological development, potentially achievable. Now let us think about a specific and underappreciated physical constraint that applies regardless of whether the payload is biological or digital: the communication problem. Go outside tonight. Find a dark place if you can. Let your eyes adjust. Give it 20 minutes. Now look up. Pick a star. Not the brightest one, not Sirius or Vega or Arcturus. Pick a dim one, the kind you might overlook. A point of light so faint it almost disappears when you look directly at it, becoming visible only in your peripheral vision. That star is somewhere between 10 and a few hundred light years away. The light entering your eyes right now left that star before you were born. Some of it left before your parents were born. It has been traveling toward you for your entire lifetime and the lifetimes of everyone you have ever known. And it arrives here, now, in this specific moment, into your specific eye. And now think about what it would take to go there. Not what the movies show. Not the jump to hyperspace, the warp bubble, the convenient technology that dissolves the distance into narrative convenience. What it would actually, physically take with the universe as it actually is. The energy required to move even a small spacecraft to that star at any meaningful speed would exceed everything humanity has ever generated, from the first fire to the last power plant, multiplied many times over. The propellant needed would outweigh the spacecraft by factors that compound with every increment of speed. The radiation encountered along the way would assault any biological passenger without pause for decades. The dust grains of the interstellar medium, barely visible individually, become dangerous at the velocities required. At high enough speeds, the universe's background radiation, the cold remnant glow of the Big Bang itself, harmless at rest, blue shifts into something lethal. And the speed of light stands behind all of this, not as an engineering barrier that better engines will eventually cross, as a structural feature of spacetime itself, written into the geometry of the universe, enforced without exception, negotiable with nothing. Hold all of that. Now hold something else simultaneously. None of what you just thought about changes what you are looking at. That faint point of light is still there. It is a real place. A star with a specific luminosity, specific surface temperature, specific mass, specific age, almost certainly with planets. Perhaps with the right conditions, distance from the star, presence of water, protective magnetic field, stable orbit, for chemistry to have organized itself into something interesting. Perhaps, in the right conditions, for something to be looking back. The physics that makes it so hard to reach also makes it exist. The same conservation laws that demand enormous energy for acceleration are the laws that made the star ignite. The same space-time geometry that limits the speed of light is the geometry in which the star formed from collapsing gas 4 billion years ago. The wall and the destination are built from the same mathematics. This is not consolation, it is something more precise than that. It is the structure of the situation. The universe built something beautiful at almost every point in space, and then built the distances that separate those points into its fundamental architecture, and then built a speed limit that ensures crossing those distances is the most expensive thing a civilization can attempt. It did not do this maliciously. It did not do this to frustrate anyone. It did not do this at all in any purposive sense. It is simply the consequence of the equations being what they are. But the consequence is this: the stars are real and close enough to see with bare eyes, and far enough away that reaching them requires everything a civilization has, and then some. Now think about what that means for us specifically. We are a species that has existed for 300,000 years. Our technological civilization has existed for perhaps 300 years in any meaningful sense. We have been to the moon, once, briefly, half a century ago. We have sent robotic probes to every planet in the solar system. Our fastest spacecraft, Voyager 1, launched in 1977, has just barely crossed into interstellar space and would need 73,000 years to reach the nearest star at its current speed. We are, in cosmic terms, a newborn. And yet we have already understood the barriers well enough to describe them precisely, to calculate the energy requirements, to identify which physical laws are doing the constraining, to propose physically grounded, if enormously challenging, approaches to crossing them. We have understood the wall well enough to know its exact shape. That is not nothing. That is, in fact, remarkable. Every civilization that has ever figured out what the wall looks like has done so from inside a single star system, with energy budgets a tiny fraction of what their star alone provides, in the first moments of their technological development. If there are other civilizations, and the size of the universe makes it difficult to believe there are not, they all faced this same moment, the moment of understanding the wall, the moment of realizing that the universe is structured to make the distances nearly uncrossable by any civilization as young as theirs. What they did next, we cannot know. Some may have turned inward, building deeper into the resources of their home system, developing civilizations of unimaginable richness within the confines of a single star's light cone, content to be infinite within the finite. The universe within a solar system, fully explored, is not obviously less interesting than the universe across multiple star systems. The possible forms of matter and energy and mind within a well-understood physical space are inexhaustible. Some may have waited, patiently, across geological timescales, accumulating the energy and technology and institutional wisdom required to eventually cross the barriers. Civilizations old enough, patient enough, and coherent enough to sustain commitment across millions of years might eventually find the barriers tractable in ways we cannot currently imagine. Some may have sent signals instead of ships, radio, laser, neutrinos, gravitational waves, some channel we have not yet discovered, filling the interstellar void with information, if not with mass, making contact through the one medium that physics allows to travel at the maximum possible speed. Some may have found something we haven't thought of. Our current physics, as we have noted, is demonstrably incomplete. The resolution of its tensions might open doors we do not currently see. And some may have run into the wall and never gotten past it, not because the physics stopped them, but because they stopped themselves, because the timescales required exceeded their institutional durability, because the resources required exceeded their willingness to mobilize them, because something else happened first. We do not know which category describes the civilizations that have come before us, if any have. We do not know which category will describe us. But here, under this specific sky, looking at this specific star, the fact of the wall and the fact of the light are both simultaneously true, both part of the same universe, both governed by the same equations. The wall is not a mistake. It is not a defect in the universe. It is the cost structure that physics imposes on crossing the distance between the places where things can happen. And the light is not despite the wall. The light is the universe doing what it does, which is to make energy and matter and space interact according to consistent laws. And those interactions over billions of years produce stars, and stars produce light, and light crosses the void at the maximum speed physics allows, and some of it, after a journey of years or decades or centuries, reaches an eye on a small planet that has only recently learned to think about why the journey took so long. The universe built the wall. The universe also built the eye that can see across it. Both of these facts are the same universe. Look at the star one more time. That faint point of light contains within it, compressed into its photons carried across the void that separates you from it, the entire story of what the universe does. Gravity pulling gas together, fusion converting hydrogen to helium and releasing the binding energy difference as radiation. Radiation crossing space at 299,792 kilometers per second, arriving here, entering your eye. You are a pattern of atoms organized by 4 billion years of biological evolution, standing on a planet made from the debris of earlier stars, looking at a light source that may have its own planets, built from the same ancient stellar debris, organized by its own billions of years of chemistry. The wall between you is real. The light across the wall is also real. The wall tells you what it costs to cross. The light tells you what is on the other side. Go inside, but carry both of those things with you. The barriers the universe built are the shape of the problem. They tell us what kind of civilization we would have to become to cross them, how patient, how resourceful, how sustained in purpose across timescales no current human institution has ever matched. We are not that civilization yet. We are the civilization that has just now understood the shape of the problem clearly enough to know what we are not yet. That is where every civilization that ever reached for the stars started.